Okay, we'll get started. We're going to start to look at AC signal in a lossless transmission line. Okay. Thus far we have seen only the DC cases, okay, the opening and closing switches, and we know many things now, but let's go ahead and look at what happens with AC signals and try to see with higher frequencies what happens, what is the impedance characteristics and impedance matching characteristics. Okay. So let's take the configuration of the transmission line where I have an alternating source. Okay. I'm going to mark this as Vs. It has a series impedance Zs, right, and it's connected to a transmission line. Okay, the transmission line has a characteristic impedance of Z0 similar to the characteristic resistance. We'll see more details about it as we go further. Okay. And the length is L, okay. And I'm going to replace the load resistor, the load impedance. Right. Okay. So we want to study this configuration and figure out what the voltages and the currents in this transmission line would look like. Okay. So we start with the wave equation, okay, for the voltage. Okay. So I have dou square V by dou Z square is equal to 1 by U square dou square V by dou T square, and the wave equation for the current will have similar form. The previous time we had written some general solutions which were very simple and straightforward to understand. It was of the form function of t minus z by u and function of t plus z by u. Okay. Here we are just going to assume that our source is going to be sinusoidal in nature. So the general forms will have slightly different format than what we saw before, but they will still be function of t minus z by u and t plus z by u. Okay. So I'll start with the general solution for the voltage. Right. First we assume that the source is going to be sinusoidal, all right. So we can say that it could be a cosine, right, and the cosine could simply be written as real part of V of z with the time dependence given by the complex exponential, right. So we want to write down V cos omega t, all right, but in order to simplify the math, we are actually writing this down as real part of V of z e to the j omega t. The reason is because I have to take 2 times partial derivatives with respect to time, all right, on the right hand side. So I know that the derivative of the complex exponential is simpler. I just have to take j omega times e to the j omega t, and each time I have to take a derivative, I have to multiply that term with j omega, that's it. So it's easier for me to do this, and in the final results one can always take the real part or the imaginary part depending upon the kind of the source. Okay. So it's just a mathematical simplification, and the I of z comma t can also be written as I of z e to the j omega t. So the time dependence is clearly periodic. Okay. Okay. Once we do this, right, we can write this down or substitute this in our wave equation, right. So we can write down dou square V by dou Z square, right hand side I will have 1 by U square, okay, and I will have j omega square for the second derivative with respect to time, and then I will have say okay. Now, since the dependence with respect to time is simply periodic, right, we can try to analyze what happens with respect to space. Okay. So, we know that it is periodic in time, the signal is periodic in time. We want to know what is it with respect to space. Okay. We know that the space coordinate and the time coordinate are coupled because there is a term velocity coming into our picture for the transmission line. All right. So, we can assume some arbitrary value of time. All right. That will simplify the amount of maths for us to write down the general solution. All right. So, we could always say that let us pick one time instant where the phase e to the j omega t, that is the omega t part goes to say 0. So, you could always substitute some t equal to 0, right, and then get rid of this term, and when you want the time dependence you can always bring back this term. Okay. So, this means that you could write this down as 1 by u square okay, and whenever I want to talk about time dependence I will multiply everything with e to the j omega t. Okay. And let us also define a new term for the quantities present over here, right. Let us say that let beta equal omega square root of LC. Okay. This will mean that the wave equation will be dou square V by dou Z square, right, because I have j square. So, I can bring the quantity to the left hand side. So, I will have plus beta square. Right. We have just rewritten the wave equation for the case when the signal is time harmonic, okay, and representing it in the form of exponentials, right, and we are taking the real part over here to simplify the math. So, the wave equation looks like this, and let us quickly do a dimensional analysis while we are at it. All right, omega square root LC. Okay. So, this has the unit of radians per meter. And it is also known as phase constant. Okay. So, when the solution, which is going to be a wave, is traveling in space, while it travels, the amount of phase it accumulates can be calculated by taking the value of beta and multiplying it with the distance it has traveled. Okay. So, the amount of phase is going to be given by the phase constant. This can also be written in a slightly different way with respect to lambda. All right. So, beta can be written as 2 pi divided by lambda. The reason why it is a constant is because the phase has to be accumulated by a number of 2 pi radians when the wave travels a distance of lambda. That is the definition of wavelength. Okay. So, depending on the value of lambda, the value of beta can change. Okay. But for a given wavelength, right, if the wave progresses in one direction with a distance equal to that of the wavelength, it will accumulate a phase of 2 pi. Okay. Now, once we have written our wave equation in a slightly simpler form, removing the time harmonic part and writing only the spatial part, we can always write down the general solution to be V of z will be V plus e to the minus j beta z plus V minus e to the plus j beta z. Okay. It is very similar to the case of forward and backward wave that we saw in the case of previous lectures, all right, albeit that now it is becoming periodic in time, and as a consequence it also seems to become periodic in space. If you look at the forward voltage wave over here, we see that it has e to the minus j beta z. That means that as you travel in the spatial direction, you will encounter some periodicity in the voltage waveform. Okay. So, anything that is periodic in time is also going to become periodic in space, all right. And here we are having the phase constant telling you how fast, the phase will be accumulated by a traveling wave in the space, right. And just like the transmission line case with DC excitation, we do have a forward and a backward wave. Okay. Okay. One could also write down the currents, how they look like. Okay. So, if the characteristic impedance of the transmission line is going to be Z naught, right, then we can just use Ohm's law and the knowledge that we already have from the previous lectures. Remember that for the backward wave, you will have a minus sign coming into the picture for the current, simply because we have discussed that the reflection coefficient for the current will be negative of the reflection coefficient of the voltage. So, some care has to be taken. So, it will mean that the forward voltage divided by the forward current will give you characteristic impedance Z naught, and the backward voltage divided by the backward current will give you minus Z naught, but one should not worry about minus Z naught as negative resistance or negative impedance, etc. It just tells you the direction of energy flow is from sink to the source, alright, not from the source to the sink. So, you should not confuse this with negative resistance, negative impedance and all that. Okay. Once we have this, we have to still establish some relationship with the solutions that we have seen in the past, alright. So, we can say that the voltage is a function of space and time, alright, that is how we started with, and the way we broke this down was it is a real part of some e to the minus j beta z times e to the j omega t. If you take the solution to the voltage, it has a magnitude mod v plus, right, and the phase dependence is e to the minus j beta z for the spatial coordinate, and with respect to the time coordinate it is e to the j omega t. Okay. So, this can be simply written as, you can take the mod v plus outside, alright, and the e to the minus j beta z can be multiplied with e to the j omega t. So, you will have e to the j omega t minus beta z, and the real part of that is going to be a cosine, right. So, you could always write down the full solution to look like cos omega t minus beta z. Okay. Now, we have to establish a clear correlation with the kind of solutions that we had seen before. So, we will just do a little bit of manipulation. Okay. So, I will just write this down as mod v plus cos, take omega outside, right. I will just do t minus beta divided by omega times z. Okay. The way we have defined beta, alright, it is omega square root LC. Okay. So, we can always go back and try to write down what this beta divided by omega will be, right. So, this will look like mod v plus cosine of omega t minus z divided by u, the velocity. Now, once again it is clear that it is a function of t minus z by u for the forward wave. So, I think that you will be able to understand that there is clearly a correlation between the kind of solution that we saw in the past and the solution for steady state AC excitation that we are seeing now. Both are, the forward case is a function of t minus z by u, the function here just happens to be cosine of t minus z by u multiplied with an omega, and for the backward wave one could establish the same, it will look like a cosine of t plus z by u. Okay. Now, since this is established, we have encountered some new terms, alright. Beta, alright, is known as the phase constant, and u has been defined as omega divided by beta. Okay. So, you will be having 2 pi radians per second, right, for the numerator and radians per meter for the denominator. So, you will end up having meters per second. This term is known as phase velocity. It just tells you that for a given wave of a specific frequency or a specific wavelength, okay, how fast it is a phase traveling, right. And when somebody defines phase velocity, automatically means that they are talking about AC excitation of a transmission line. Otherwise, in DC you will not talk specifically about phase velocity, you will be talking just about the velocity, all right. So, this omega divided by beta, if it is referred to as phase velocity, they are talking about AC excitation of a transmission line. Okay. Since we are aware of the general solution to that lossless transmission line for AC excitation, right, we can always go ahead and try to see what will be the equivalents of what we saw for the DC excitation, that is terminations, open circuit, short circuit conditions, reflection coefficient. These are the conditions that we need to see. Okay. So, we can start with a setup, right. So, as usual we will forget the source part. Okay. So, we will start with some terminations. I will have a transmission line, okay, and let us say its characteristic impedance is Z naught, right. Phase constant is beta. I have a load resistor ZL. There are too many Z's, but the Z that I am writing below is the spatial coordinate. Okay. So, if you look at the spatial coordinate convention, it is slightly weird. Okay. Z equal to 0 corresponds to the load end and Z equal to minus L corresponds to the source end. You can use any other convenient system for spatial representation. I am doing this simply because I am interested in finding out the reflection coefficient at the load end. So, gamma suffix L, what we had seen before, is what I want to find out. If the position is 0, I can get rid of many terms in my mathematics. So, I am just doing a simplification over here. So, it is not uncommon to find slightly different coordinate definition system. Usually people will start with Z equal to 0 on the left hand side, Z equal to L on the right hand side. Anything is okay as long as you are consistent with it. There are no hard rules regarding this. Right. If we did do this, all right, we can say that the voltage at Z equal to 0, okay, the voltage at Z equal to 0 will correspond to the load voltage, all right, is equal to the current that is flowing in this branch with the impedance ZL multiplied by the ZL itself. So, you are applying Ohm's law at the load end, V is equal to I times Z. Okay. So, it is going to be I at Z equal to 0 multiplied with ZL. Okay. And at the position Z equal to 0, you will be having a forward and a backward wave. If you have a look at the solutions that we have written, we have V plus e to the minus j beta Z, Z is equal to 0 makes this term equal to 1. So, that makes my math simpler and hence the choice of the coordinate system. V minus e to the plus j beta Z, once again Z is equal to 0. So, the math becomes simpler over here. So, at Z equal to 0, I can write down the voltage to be V plus V minus, right. So, I can just write this as some magnitude. This is at Z equal to 0, V naught plus V naught minus is going to be equal to, okay. Now, we have to write down the expression for the current. The current depends on the characteristic impedance of your transmission line. So, you have to look at the expression that we have written before. So, it is 1 by Z naught V naught plus minus V naught minus times ZL. Okay. This is the expression for this is the expression that we are getting from Ohm's law on the load end of the transmission line, and we are interested in finding out the ratio of V naught minus to V naught plus. Okay. It is a simple rearrangement, right, and you will end up getting ZL minus Z naught by ZL plus Z naught. This is very similar to the reflection coefficient that you got for the DC excitation. There it was RL minus RC divided by RL plus RC in our lectures. Here it is simply ZL minus Z naught by ZL plus Z naught, all right, and we will call this as gamma. And to say that it is gamma at the position of the load, we just replace it with the suffix of L to just say that it is a load. Sometimes these conventions can become confusing, especially when you have the length marked as minus L and all that. So, it is okay to be very specific, you can always say gamma at, it's okay, right. Okay. Now, compared to the previous case where gamma was RC minus RL minus RC by RL plus RC, here we are having ZL minus Z0 by ZL plus Z0, the most generic case. It means that each of the quantities ZL, Z0, etc. can actually be having some component of resistance, some component of inductance, some component of capacitance, etc. All right. However, we are considering some lossless transmission line in this case. So, we have still not attached our series resistance to the inductor, parallel conductance to the capacitor yet. Okay. So, the solutions are slightly easier. Okay. And the other thing that we need to start looking at is what will happen in the transmission line when the termination is extreme. Say for example, it is a short circuit or an open circuit. These are the two cases that we have seen for the DC excitation. You will see the same case, and on top of that there is something funny happening with respect to the impedance in the transmission line. We will have to look into that. Okay. So, we will start with the case where the transmission line load end is open circuited. Okay. Okay. When ZL is equal to infinity, V of Z is going to be V naught plus e to the minus j beta z plus V naught minus divided by V naught plus e to the plus j beta z. So, I have written in this form so that I can substitute for V naught minus divided by V naught plus as gamma L. Okay. So, when it is open circuited, this is going to be the reflection coefficient is going to be equal to 1. Okay. So, I can just substitute 1 for the reflection coefficient and I end up getting V naught plus e to the minus j beta z plus e to the plus j beta z. So, sum of two complex exponentials which are alternating in sign, means you will end up getting a cosine. Okay. So, we will be having, this is going to be equal to 2 V naught plus cos beta z. Okay. Now, this is a very important thing to look at, right. It means that the voltage at any position z in the transmission line, okay, will vary as 2 V naught plus cos beta z, where z is taken from the load towards the source end. But what it also means that there are values of z where the voltage in the transmission line is going to be 2 times your forward voltage reaching the load end. Okay. So, the maximum rated voltage for a transmission line should always be considered based on the superposition of your forward and backward travelling wave. So, the peak voltage at specific positions at the transmission line can be double. Okay. Similarly, if I wanted to calculate the current in the transmission line at a position z, I can use the expression for the current from the general solution. So, I have V naught plus divided by Z naught. Okay. So, I am having V naught plus divided by Z naught multiplied by some exponentials, but I do have the minus sign here to indicate that it is current reflection coefficient is negative compared to the voltage reflection coefficient. So, here once again you can substitute gamma L and you get a difference between two complex exponentials, right, and you can write this as some sign, right, sinusoid, right. So, in this case it will be looking like minus j 2 V naught plus divided by Z naught sin beta z. So, when your load is open circuited, depending upon the position, all right, you will have a voltage going with the form 2 V naught plus cos beta z, and the current is going to be minus j 2 V naught plus divided by z naught sin beta z, all right. In this case, there are a few things that should be very clear. Okay. First of all, as you go along the distance of the transmission line, there are going to be specific places in your transmission line, for example, z equal to 0, all right, and then beta times z is going to be some multiples of 2 pi or pi. You will have repetitions of the voltages occurring in your transmission line. So, it will be repeating again and again and again, all right. The peak value of the voltage that can happen in your transmission line is 2 V naught plus. The current is minus j 2 V naught plus divided by z naught sin beta z. So, it is also periodic. The only thing that we notice is there is a phase difference between the current and the voltage. Okay. This j should signify something. Okay. It should signify something. So, if you take the ratio of voltage to current, we know that we will get impedance. It is telling us something about the impedance, and then the current and the voltage are out of phase, etc. Okay. So, if we want to have a closer look related to the impedance, we need to write down the expression for V of z divided by I of z, and then we need to see how the impedance in this line will change. We already have a very good guess, all right, cosine of beta z divided by sine of beta z, all right. So, there is a good possibility that at position z equal to 0, the denominator will become 0 for the expression for your impedance, and it is going to look like it is infinity, but there is going to be another place where the numerator is 0, all right. So, you will be having z equal to, the impedance is equal to 0, etc. So, we need to be clear about what is the distribution of impedance in the transmission line, and we need to derive some meaning from it. Okay. So, in order to make this problem a little bit clearer, okay, we will draw the entire system with the source. Okay. So, I will be having Vs, I have a series impedance Zs, I have a transmission line, I have a load impedance ZL, okay. The length of the line is L, and I am maintaining the same coordinate system, which means that I am going to mark the load end to be position Z is equal to 0, position Z is equal to minus L. Okay. The characteristic impedance of the transmission line is Z naught, and the phase constant is beta. I want to understand, looking into this transmission line, what is the impedance that I will be seeing, right. So, if I look into the transmission line towards this direction as marked in the arrow, I want to understand what is the impedance that I would be seeing. Okay. So, let us take the scenarios. So, I can start with the expression for what will happen at the input. So, it is V at Z equal to minus L in our expression, right. So, I am just going to write this down. So, V is equal to minus L. So, I have V naught plus e to the plus j beta L, okay, minus j beta times minus L, right, plus V naught minus divided by V naught plus the minus j beta capital L. So, I have just taken the expression for the voltage general solution with respect to space, substituted Z is equal to minus L, telling that I am looking at the input end. Okay. So, this is the expression for the voltage, and I could be clearer and write this down as V naught plus times e to the plus j beta L plus gamma suffix L e to the minus j beta L, where gamma suffix L is the load reflection coefficient. The current at the input end of the transmission line is going to look like V naught plus divided by Z naught e to the plus j beta L minus right, and all I have done is substitute Z is equal to L in the general solution for the voltage and the current, not done anything more than that. I just want to take their ratios and I want to understand what the impedance will look like, right. Right. So, I can take the ratio of V at minus L to I at minus L, right. So, I am going to be ending up with Z naught ZL plus J Z naught okay. I am not doing the detailed simplification process, it is just sum of complex exponentials and difference between complex exponentials, you can do it by yourself. So, the rearrangement looks like Z naught multiplied by ZL plus JZ naught tan beta L divided by Z naught plus JZL tan beta L. This is actually a very complicated expression, okay. It is a very complicated expression, and one cannot get a feeling of what the Zn is actually going to look like when the transmission line is of length L. But one thing is clear, if the transmission line is of length L, all right, even within that transmission line you are going to have some repetitions that are happening. So, because these are trigonometric functions, they do have a period, all right. All that matters is beta L within your brackets for the trigonometric function, it does not matter what your L is. So, it is going to be repeating every once in a while. So, it clearly justifies that if I take a small section of the transmission line and if I understand its properties from say beta L is equal to 0 to beta L is equal to 2 pi, I would have understood what all the transmission line can do. So, for this reason the term beta L is usually known as electrical length. Okay. The term beta L is known as electrical length simply because it just tells you the phase between 0 and 2 pi. Okay. And we started our original derivations for the case when the load impedance is going to be infinity or open circuit. So, here we can do the same thing, ZL is equal to infinity, that is the case we started with open circuit load, right. If this is the case, right, you can express Zn. So, common mistake that people do is substitute infinity plus something divided by Z naught plus infinity. Whenever you have infinity coming in, that means that you have to take it to the denominator somehow. So, you can divide the numerator with ZL, denominator also with ZL, that way you will have Z naught by ZL and ZL by ZL in the denominator will become 1, alright. So, if you did do that, okay, you will have Z naught minus J cotangent also one can say that it is minus J Z naught cotangent of beta L, which is once again a very complicated expression. This means that as you change the electrical length of your transmission line, the input impedance for the transmission line with same characteristic impedance is going to be dramatically different, okay. And one could just simply draw a plot for what the cotangent would look like, okay, as you change the electrical length. So, you can always draw an axis, right. The x axis can be your say beta L, your y axis can be minus Z naught cotangent of beta L, all right. So, you will have at beta L equal to 0, tangent will be equal to 0, cotangent will become infinity, because we have a minus sign in front of it, all right, we will be having minus infinity, all right. Let us for now forget about this J, all right. Let us just understand that the Zn is purely reactive, okay, does not have any resistive part, that is what this J is telling us, all right, and minus J Z naught cotangent beta L. If this entire quantity inside, that is say this square bracket becomes positive, then Zn will look like minus J something. It is similar to seeing a capacitance, right. If the term inside the bracket is positive, then you will see capacitance. If the term inside the bracket is negative, Zin will look like an inductance, alright. It is also possible because it is a cotangent beta L, it passes through zeros. There is quite a possibility that your Zin will look like a 0 or a short circuit. So, it can go from minus infinity to plus infinity passing through 0. So, a section of the transmission line can have variety of impedance depending on how the electrical length of the transmission line is, right. So, in this case you will go from minus infinity to say steadily some lambda over 4, alright. So, this will be or pi by 2, okay. And then you will have this rising up, okay. And then there will be a discontinuity, okay. This will correspond to lambda over 2 or pi, alright. And then once again 3 lambda divided by 4, right. And then there will be a discontinuity corresponding to lambda. Lambda is the wavelength, okay. Pi by 2, pi, 3 pi by 2, 2 pi. I have just marked the x axis to be electrical length going from 0 to 2 pi. It means that the Z in that I will be seeing, right, in the transmission line, this is going to be your 0 on the y axis, right. It will be negative. So, this means that in this region where your Z in is going to be negative, the equivalent circuit of your transmission line as seen from the input side is going to look like a capacitor, that is all. Alright. So, if you try to make inferences about your transmission line from the input end, you will be measuring some negative imaginary part, alright. So, you can just write this down, the equivalent circuit to be a capacitor, okay. In this place it is capacitor. If you were to look at the part where the minus Z naught cotangent beta L is negative, or net input impedance is positive, the equivalent circuit will be like an inductor, alright. So, if you were to make derivations on the transmission line only based on looking at the input impedance, you are not talking about RL, GC, etc. You are just looking at a transmission line of some length L with an electrical length of beta L, right. Its equivalent circuit characteristic, a single lumped element, if you have to place and try to do your analysis for the circuit, it will look either like a capacitor if you measure the value to be a negative imaginary part, it will look like an inductor if it is a positive imaginary part, and there are some absurd things that are happening. So, the zero crossing has to be very clear. Right. There are some zero crossings. In the zero crossing, it means that the impedance is 0 or it is a short circuit, that is your current is going to peak. Okay. In those cases, the equivalent circuit where the current is going to peak is going to be a series combination of L and C. If you have series combination of L and C, and if your inductive reactance matches the capacitive reactance, alright, then you will end up having a short circuit and your peak voltage is going to be just source voltage divided by source resistance, okay, that is going to be your peak. So, the equivalent circuit at the place of zero crossings is going to be L in series with C. Then we also have to talk about the equivalent circuit at the place of discontinuities, that is you are having plus infinity to minus infinity going in your y axis for the input impedance. In those cases, it will be a parallel combination of L and C. Okay. So, it is very important to know this, that a section of a transmission line which is lossless, depending upon how long it is, could act like an inductor or could act like a capacitor, could act specifically like a series combination of inductor and capacitor or a parallel combination of inductor and capacitor. So, that means the technology for making any of the passive circuit in high frequencies is the same. You need to know how to make transmission line, that is it. The remaining job is where to cut the transmission line so that you can make any of these passive components. When we began this course, we began by saying that the equivalent circuit of the transmission line is going to be some chopped up versions of L and C arranged together, alright. But it is also true that if you were to replace a transmission line with a lumped element, this is how one could do it, alright. So, it means that the technology for making inductor is not different from the technology for making capacitor. You will be making the same transmission line in your manufacturing company, but depending on the requirement for that particular case, you will be precisely dicing or cutting your transmission line to where you want, alright. So, it means that I can have LC and parallel combination of L and C. So, you could build a lot of circuits with this, alright, and all you will need is transmission line and cut with different sections. Just to be complete, I will also write down the short circuit condition, that means ZL is equal to 0. So far we have seen the case with open circuit. See the short circuit case, right. The short circuit case is going to be Z in is J Z naught tan beta L. This means that in the expression for Z in, which was Z naught times ZL plus J Z naught tan beta L, this is the expression, you will substitute ZL is equal to 0 and you end up with J Z naught tan beta L. Once again you can draw the variation of Z in with respect to the electrical length beta L. It will also have some places where it goes to plus infinity and minus infinity discontinuity and some 0 crossings, alright. And you will notice that the impedance of the transmission line is repeating every lambda over 2, okay. Every lambda over 2 it will keep repeating. And the special case is where you have ZL is equal to Z naught, Zn is going to be equal to Z naught. This is a special case because if your load impedance is the same as your characteristic impedance, no matter how long or how short your transmission line is going to be cut, no matter what, at the input you will see only characteristic impedance Z naught, okay. It will look like it is purely resistive, okay. ZL will be equal to Z naught, alright, and the unit of Z naught is simply ohms and it is square root of L divided by C in ohms. So, if you have a lossless transmission line, alright, and excited by a AC source, and if ZL is equal to Z naught, no matter what electrical length you take for your transmission line, at the input side you will measure only Z naught. So, this means that I now know how to create different impedance profiles by making use of this, right. Suppose I wanted to manufacture a high frequency circuit, I could make use of these properties to replace some inductors, some capacitors, some combination of inductors and capacitors, and I could also target some specific values of Z in equal to Z naught to fill up some purely resistive branches of your circuit. Okay. But this is not very convincing because although we have made L and C very easy, resistance is not something that is coming into the picture, alright. So, the only way to go forward is to actually introduce a different phenomenological model. So far we have been using a lossless transmission line with L and C. We have to be a little bit more practical, include a series resistance in the inductor branch, include a parallel conductor and redo whatever we have done, and then we have to see what the consequences would be. So, thus far the procedure for analyzing the circuit is very much the same as in DC. You can calculate the load reflection coefficient as ZL minus Z naught by ZL plus Z naught, and depending upon the termination you will be able to find out what the reflection coefficient is going to be. But the only difference with respect to DC over here is that depending upon the position you will have places where your transmission line is always having 0 voltage or always having 0 current, etc. The impedance in your transmission line will be varying from one place to another place depending upon the electrical length. Okay. These are some of the subtle differences. The program that we have written, you can always substitute a cosine or a sine and try to see what happens. Here, mind you, we have considered only the spatial distribution. We have still said that with respect to time, it is going to be time harmonic or periodic. So, it means that even though you will have some places in your transmission line having non-zero voltage, with respect to time, it will go to a maximum and then go to 0. With respect to time, it will go to maximum and go to 0, but the nodes where it is 0 is going to be fixed all the time. So, some small things will appear only if you take that simulation that we had already done and plug in a cosine or a sine just to understand what that means. Okay. So, in these cases, even though you have a AC input excitation, we do have fixed places on the transmission line where the voltage is going to be 0 or the current is going to be 0, all right, and you are going to be having fixed positions where the voltage or currents are going to become maximum. So, we call these kinds of waves as standing waves. Okay. And soon we have to analyze the meaning of this standing wave. Does it tell you anything about the termination? Can any more information be arrived at? What is the consequence of standing waves on the power to be delivered? All these things has to be seen. So, we will go forward in that direction. I will stop here.